Assalamualaikum warahmatullahi wabarakatuh. Hello everybody. How's life? I hope you all in a good health. In this video, the first group will present to you about elementary function part 2. First, introduce the member of group 2. The members are Yuslia Irawati, Chatarina Mauren M.P, and Anifa Mirza Liadiani. In this video, we will present to you about hyperbolic function, inverse trigonometric function, and inverse hyperbolic function. Here the first material, hyperbolic function. The hyperbolic sine and cosine of a complex variable are defined as sine hyperbolic z is equal to exponential z minus exponential negative z over 2, and the cosine hyperbolic z is equal to exponential z plus exponential negative z over 2. Since exponential z and exponential negative z are entire, then sine hyperbolic z and cosine hyperbolic z are entire also. Furthermore, the derivative of sine hyperbolic z to z is equal to cosine hyperbolic z, and the derivative of cosine hyperbolic z to z is equal to sinus hyperbolic z. Because of sine z is equal to exponential iz minus exponential of negative iz over 2i, and cosine z is equal to exponential iz plus exponential of negative iz over 2, the hyperbolic sine and cosine functions are closely related to those functions. Negative I sine hyperbolic of iz is equal to sine z, and cosine hyperbolic of iz is equal to cosine z. And then the negative I of sine iz is equal to sine of hyperbolic z, and cos iz is equal to cosine hyperbolic z. There are some of most frequently used identities involving hyperbolic hyperbolic sine and cosine. In here, sine hyperbolic of negative z is equal to negative sine hyperbolic z, and cosine hyperbolic z, cosine hyperbolic negative z is equal to cosine hyperbolic z. And then the cosine hyperbolic square, or the square of hyperbolic the square of cosine hyperbolic z minus the square of sine hyperbolic z is equal to 1. And the sine hyperbolic of z1 plus z2 is equal to the sine hyperbolic of z1 times the cosine hyperbolic of z2 plus cosine hyperbolic of z1 times sine hyperbolic z2. And then the cosine hyperbolic of z1 plus z2 is equal to cosine hyperbolic z1 times cosine hyperbolic z2 plus sine hyperbolic z1 times sine hyperbolic z2. And then in here, sine of hyperbolic z is equal to sine hyperbolic x cos y plus I cosine hyperbolic x times sine y. And for cosine hyperbolic z is equal to cosine hyperbolic x times cosine y plus I sine hyperbolic x sine y. And in here, for the square of absolute value of sine hyperbolic z is equal to the square of sine hyperbolic x plus the square of sine y. And for the square of the absolute cosine hyperbolic z is equal to the square of sine hyperbolic x plus the square of cosine y. In view of periodicity of sine z and cosine z, it follows that sine hyperbolic z and cosine hyperbolic z are periodic with period 2pi. Sine hyperbolic z is equal to 0 if and only if z is equal to npi, for n is an integer. And cosine hyperbolic z is equal to 0 if and only if z equals to p over 2 plus np times 2i, with n is integer. The hyperbolic tangent of z is tangent hyperbolic z equals to sine hyperbolic z over cosine hyperbolic z, and is analytical in every domain in which cosine hyperbolic z not equal to 0. The function of cotangent hyperbolic z, secant hyperbolic z, and cosec hyperbolic z are the reciprocals of tangent hyperbolic z, cosine hyperbolic z, and sine hyperbolic z respectively. And in here, we have an example. Determine z such that cosine hyperbolic z is equal to half. For the solution, before we have known that cosine hyperbolic z is equal to exponential z plus exponential negative z over 2. Therefore, in here, exponential z plus exponential negative z over 2 is equal to half. And then we get that exponential z plus exponential negative z is equal to 1. Then we multiply all sides with exponential z. Then we obtain that exponential 2z plus exponential 0 is equal to exponential z. And we move the right side into left side, and then we get the exponential 2z minus exponential z plus 1 equals to 0. After that, we let after that, let exponential z equals to t. Then obtain t squared minus t plus 1 equals to 0. Using quadratic equation, we get the t1, t2 is equal to 1 plus minus I the square root of 3 over 2. Then we get if exponential z is equal to t1, this is equals to 1 plus I square root of 3 over 2. Or if the exponential z is equal to t2, this get 1 minus the square root 3, the square root of 3, or if the solution, or when the exponential z is equal to t2, then equals to 1 minus I square root of 3 over 2. Then we can find the z value. For the t1 equals to, for the t1, z is equal to the ln 1 plus I square root 3 over 2. Or for t2, z is equal to ln 1 minus I square root of 3 over 2.
Inverse trigonometric function. Inverse of trigonometric function can be described in terms of logarithms. Define the inverse of sine function as w equal to inverse of sinus z, when z equal to sinus w. Then z equal to exponential iw minus exponential negative iw over 2i. Name it as expression 1. From 1, we can express in the form of z. We do cross multiplication, and for each side, we multiply with exponential iw. Then we will get it is equal to exponential iw square minus 2iz exponential iw minus 1 equal to 0. It is equivalent to exponential iw minus iz square of equal 1 minus z square, equivalent to exponential iw equal to iz plus 1 minus z square over a half. Name it as expression 2, where 1 minus z square power a half is a double value function of z. Taking logarithms of each side of expression 2 and recalling that w equal to inverse sinus z, we get that inverse sinus z equal to negative I log of iz plus 1 minus z squared power a half. Name it as expression 3. Here, we have that inverse sinus z is a multiple value function with infinitely many values at each point c. Next, we will show that it is multiple value function. In a example, based on expression 3, for inverse sinus negative I, we will get that inverse sinus negative I equal to negative I log of 1 plus minus square root of 2. For the first, we will have log of 1 plus square root 2 equal to ln 1 plus square root 2 plus 2n pi, when n equal to 0, plus minus 1, plus minus 2, and so on. Second, you have log 1 minus square root 2 equal to ln square root 2 minus 1 plus 2n plus 1 pi, where n equal to 0, plus minus 1, plus minus 2, and so on. Since ln of square root 2 minus 1 equal to ln 1 over 1 plus square root 2 equal to negative ln of 1 plus square root 2, then the numbers negative 1 power n times ln of 1 plus square root 2 plus n pi when n equal to 0, plus minus 1, plus minus 2, and so on constitute the set of values of log 1 plus minus square root 2. Thus, in rectangular form, inverse of sinus negative I equal to np plus I times negative 2 power n plus 1 times ln of 1 plus square root 2, where n equal to 0, plus minus 1, plus minus 2, and so on. We can apply the technique used to derive the expression 3 for inverse sinus z to show that inverse cosine z equal to negative I log of z plus I times 1 minus z squared or a half. Name it as expression 4. And for the inverse tangent z equal to I over 2 times log of I plus z over I minus z. Name it as expression 5. These functions are also multiple valued. When specific branches of the square root and logarithmic function are used, all three inverse functions become single-valued and analytic because they are then composition of analytic function. The derivatives of these three functions are readily obtained from logarithmic expression. The derivative of the first two depend on the value chosen for the square root. 1. Derivative of inverse sinus z equal to 1 over 1 minus z squared or a half, named as expression 6, and derivative of inverse cosine z equal to negative 1 over 1 minus z squared over a half, name it as expression 7, and the derivative of last one as derivative of inverse of tangent z equal to 1 over 1 plus z squared.
We will discuss the inverse hyperbolic function. The first one is the definition of inverse hyperbolic function. There is three definitions, that is definition for sinus, and then definition for cos, and the last is definition for tangent. For the definition of sinus, that is sinus power minus 1c equals to ln c plus square root of c squared plus 1. And then the definition for cos is cos power minus 1c equals to ln c plus square root of c squared minus 1. And then the last is the definition for the inverse of tangent, that is tan power minus 1 c equals to a half ln 1 plus z over 1 minus c. And from the definition, we have function branch with two value, that is square root of c squared plus 1 and c squared minus 1 respectively, from definition of function sinus power negative 1c and cos power negative 1c. Now we will discuss function branch with two value square root of c. By change square root of c into exponential form, we get c equals to square root of r e power I theta. So fc equals to square root of c and equals to square root of r e power I theta. For 0 less than theta less than 2p, this function is f1c and f2c. For f1c, it is equals to square root of r e power I theta, and for f2c equals to negative r square root of r e power I theta, and it is equals to negative f1c. So here we have two values. Function f1c equals to square root of r e power I theta in the domain r more than or equal 0 and 0 less than or equal to theta less than or equal to 2p, continue in c equals to 0. But we can prove that it is not differentiated in c equals to 0. And we will prove that f1 is not continue in positive real set. Given any positive real number co minus ro e power I theta o with ro greater than 0 and theta o equals to 0. If c approaches co from above real axis, then f1c approaches to square root of ro. If c approaches co from below real axis, then f1c approaches ro times e power I p, and it is equals to negative square root of ro. Because both limit value are different, so f1c don't have limit for c approaches to co. Thus, f1 is not differentiated in c equals to 0 and c more than 0. From the explanation, we get function f1c and f2c in the domain c are where r greater than 0 for 0 less than theta less than 2p is the branch function from function with two value fc equals to square root of c. Here, the way to prove f2 is same with the way to prove in f1, so we don't need to the proof. The next, we know that f1 and f2 are branch from square root of c in the domain c where r more than 0 and alpha less than theta less than alpha plus 2p for any alpha. Thus, we can conclude a function with one value f for every point c element of complex number, where the value of f set is one of the value of square root of c, so f is the branch from square root of c with the branch intersection consists of 0 point f and points where f is not continuous. So that's all the presentation from us. Thank you for watching this video. Hope it will be useful for you. Thank you.